So we'll take a few minutes to talk about a problem from the 2009 AB as well as the BC exam. This was problem number one on each of those exams. It's a calculator problem. And the setup for the problem is that we've got a velocity graph given here. The one thing that you've got to kind of be careful of is the scaling on the y-axis here. We'll have a couple different places within this problem where that can definitely trip us up a little bit if we're not careful with it. But situation described is that Karen rides her bicycle on a straight road from home to school. She starts at home at t equals 0 and arrives at school at t equals 12. During the time interval 0 to 12, her velocity is measured in miles per minute and indicated by the velocity function that we are given a graph of, and that's a piecewise linear function. So everything that we see here is a line. We, in part A, are asked to find the acceleration of her bicycle at time t equals 7.5 minutes, and then to indicate units of measure. So if you think about the relationship between velocity and acceleration, we would take the derivative of velocity to develop an acceleration function. So what we have to do in part A here is we have to use a function to determine values of that function's derivative, and hopefully that triggers for you slope of the tangent line. Well, if you look at the value of 7.5 on the t-axis here, you need to know what the slope of the tangent line to this velocity graph is at t equals 7.5. And if you look at the portion of the graph that goes from the t-value of 7 to the t-value of 8, that is a line. So the slope of the tangent line connecting those points is going to be the same as the slope of the line itself. So the thing that could get you into a little bit of trouble here is if you just did a rise over a run, -1 divided by 1, it's easy to say that her acceleration was -1. But here's where the units come in, right? The y value here, the velocity value at 7 was 0.3. The velocity value at 8 was 0.2, and then when we divide by 7 minus 8, we end up with -0.1. You can toss this into the calculator if you're concerned about getting that numerical value. And then what are the units? Well, if you think about the units of the 0.3 and the 0.2, those are units of velocity being measured in miles per minute. And then we're dividing by the units of 7 minus 8. Well, 7 and 8 are both being measured in minutes. So we've got miles per minute, or miles per minute squared. If you check out Part B says that we should use correct units to explain the meaning of this expression in the terms of Karen's trip. Find the value of that expression. So if you think about the absolute value of velocity, what we've done off and on this year is we've defined the absolute value of velocity to be speed. And if you integrate speed, or integrate the absolute value of velocity from 0 to 12, what really ends up happening with all of your function values, all of your velocity values that are negative, and they really only sit right here on your graph, they all are going to get reflected across the t-axis up into the first quadrant in this case. And what that means is that all of the area that would be accumulated by this function, absolute value of v of t, between it and the t-axis is going to be above the t-axis. So this is really like a total area calculation on a velocity curve. And if we think about how we would be impacted by the velocity function ending up inside that set of absolute values, if it was the velocity function without absolute values inside the integral, we'd end up with a change in position. But whenever we throw the absolute values there, we're considering this change to be positive, this change to be positive, all of this change in position to be positive. So what we end up with is we're going to end up with the total miles that Karen has traveled after leaving home before she arrives at school. The value of that integral, it's just going to be area arguments. You see down here I've got 1/2 base times height, 1/2 base times height, 1/2 base times height. Length times width, I've got the average of the parallel sides divided by the times the distance between them, length times width, and then 1/2 base times height again. So basically I just did triangle here, find the area, triangle here, find the area, had a triangle here, rectangle sitting right here, a trapezoid sitting right here. Here we have a rectangle with a width of 3, and then right here we have a triangle. So I just found the area of each of those geometric figures. You do notice that I have a bunch of decimals within these computations. And here's another place where you've got to be careful with the scaling on the y-axis. On this first triangle right here, it has a base of 2 units. Its height, the altitude to that base, wouldn't be 2 units, it would be 0.2 units. So the area of this triangle right here is going to be 1/2 base times a height of 0.2. So just be careful with your heights there. Make sure you're using the decimal representations. And if you do, and you throw this expression into the calculator, you're going to end up with 1.8 for the value of that integral. In part C, it says that Karen realizes she left her calculus homework at home, returns to get it. At what time does she turn around to go back home? Give a reason for your answer. So the easy mistake to make here is to look at this graph and say, well, the graph changes directions right here at the t-value of 1, so that must be when Karen turned around to go home. Well, velocity is positive, 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 still positive, 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 positive. Here's where velocity is 0. And then on the other side of the t-value of 2, we see negative velocity. So when velocity is positive, that indicates that position is increasing, and the position is increasing from 0 until 2. The position doesn't start to decrease, and she doesn't start to move back home until we start to see some of those negative velocities on the other side of the t-value of 2. At the t-value of 4, we see 0 for velocity. So during this minute stretch of the graph, that must be when she was in her house getting her homework. She's not moving back towards school yet. And then she moves back towards school, positive, 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 positive velocities for the rest of the graph before she arrives at school at time t equals 12. So the little rate up I have here, she turns around at time 2, since velocity changes from positive to negative. And when velocity is positive, we're looking at an increasing position. When velocity is negative, we're looking at a decreasing position, and that's why we know she turns around to get her homework at t equals 2. And then the last piece of this says that Larry also rides his bicycle on a straight road from home to school, and it takes him 12 minutes. His velocity is modeled by the function w of t. So this represents Larry's velocity at any time on the trip from home to school, also being measured in miles per minute. Who lives closer to school, Karen or Larry? Show the work that leads to your answer. Well, based on what we just said in part C, to figure out how far Karen lives from school, what we're going to need to do is we're going to need to know how far she traveled from the t-value of 5 to the t-value of 12, because this is when she leaves home after retrieving her homework and then makes her way back towards school. Here's when she arrives at school. So the total distance that Karen lives from school is whatever the area between the velocity graph on the interval from 5 to 12 and the t-axis is. And if you use area arguments to determine that, you've got a triangle here, you've got a rectangle from 6 to 7, you've got a trapezoid from 7 to 8, you've got a rectangle from 8 to 11, you've got another triangle from 11 to 12. You can find the units of each of those triangles, trapezoids, rectangles, find their areas and sum them. And what you end up with is you end up with 1.4 miles. If you wanted to take a sneakier approach to determining that value, we knew that the total area of this triangle and this triangle summed with the area that sits here, we know that's 1.8 square units from our answer to a previous piece of the problem. We're not going to count the distance she traveled here minus the distance she traveled here to go back home and get her homework. So the area of this triangle and the area of this triangle would be subtracted off of that 1.8 value from a previous part. Or you can do what I mentioned a minute ago and you end up with 1.4 for the distance that Karen lives from school. What I did with Larry's velocity graph, I just graphed it on the interval from 0 to 12. I just wanted to confirm that Larry doesn't turn around to get his homework like Karen did, and we do see positive velocities, positive values for W on the interval from 0 to 12. So Larry doesn't do any turning around to go home to get his homework. So the integral from 0 to 12 of W of t is going to indicate the distance Larry lives from school. And to find the value of this integral when the calculator's in play, you can do the integral from the graph screen, you can do the integral from the home screen out of the math menu, and if you do that successfully, as long as you're in radian mode, what you end up with is you end up with 1.6 for the value of this integral. So Larry lives 1.6 miles from school. Karen lives 1.4 miles from school, so obviously Karen lives closer to school. Easy mistake to make is to take your answer from part B and say that Karen lives 1.8 miles from school, but we don't want to count any of the portion of the graph where she was going to school and then returning home to get her homework. We just want to count the portion of the distance from when she left to go back to school to when she finally arrived at school.